So we have one presentation in this session. It's 55 minutes long. Our speaker is going to be Bryan from Rose-Hulman Institute of Technology, and he's going to tell us about introducing ODEs through modeling and applications.
Thanks. Can everybody hear me? Okay, I'm going to share my screen now and make this full screen. Okay, everybody can see that? Okay, so what I want to do is I've got two different modeling scenarios that I want to show you that both of them are actually in the Simio book, ODE book that I wrote. These are ones I've used many times in class. So I want to start with the first one is the so-called Hillkeller model. This is one I often kick off my ODE 1 class with. So here's a picture from the 2008 Olympic 100-meter final. The guy in front is Usain Bolt, who won the race and set a world record in the process. He set a world record of 9.69 seconds, and he was so far ahead of the field, as he was often did in races. He would actually ease up in the last 20 meters and look back at the field and smile. And so he done that on a number of races. From 50 to 80 meters, he averaged 27.3 miles an hour. So it's an astonishingly fast race. The goal is to devise a mathematical model of not just Usain Bolt's progress down the track, but any sprinter running in something like a 100-meter race, a 50-meter race, 200 meters, something like a sprint. And we'd like to model how they progress down the track using basic physics. And this might give us a way to predict how fast they could run other distances, to decide which world records are, as they say, soft, that is, slower than expected and right for braking, or could we even recommend strategies for running even at longer distances? Well, we're going to devise a model for a sprinter's progress down the track, and we're going to use data from Usain Bolt's 2008 Olympic gold medal race. And there's the data right there. It comes in time, position, pairs. You can see at the start of the race, when he was at the starting line, it took him 0.165 seconds to react to the starter's gun. And then at 10-meter intervals down the track, we have the time he passed that point to 100th of a second. So this is data we can use to test our model and validate it. Here's a plot of the data as he progresses down the track. You'll see that again later after we have a model to fit to it. So here's the model. When I do this with students, I kind of do a back and forth in the classroom. I want to lead them to what's called the Hillkeller model, but I don't want to be, I'm somewhat heavy-handed about it when it's their first attempt at doing something like this. But at the same time, I want their input so they see where some of these assumptions come from. First of all, T is time, X of T is Bolt's or the sprinter's position on the track. X equals 0 is the starting line. X equals 100 is the finish in a 100-meter race. I want a model that's grounded on basic physics, specifically Newton's law of motion, and I want it to be adaptable to different sprinters. So we're going to use V of T. Really, V of T is going to be the primary function we're interested in initially. That's going to be the velocity of the sprinter. We're only interested in horizontal motion. And as I said, X equals 0 is the starting line, and progressing down the track to X equals 100 at the finish. So the heart of the model is going to be Newton's second law of motion, F equals ma. And so the students I teach have all taken physics, so they have seen that. And so I say, what's A in terms of V? If V of T is the function we're looking for, what's A? They say, well, it's V prime. So we can write down mv prime equals force on the runner. I write F net for the net horizontal force on the runner. And now the interesting part starts. What is the net force on the runner? What kinds of things factor into that? Well, in the Hillkeller model, it's entirely sensible. The net force on the runner is broken into two kinds of forces: propulsive force that propels the runner down the track, and resistive forces that impede the runner's progress down the track. And so our goal is to quantify those two forces using reasonable assumptions and whatever data we might have. Like you'll see, they depend on the mass of the runner. So how can we, first things first, the propulsive force that the runner exerts to propel themselves down the track. How can we come up with a meaningful model for that? Well, I query the students, what are some forces that propel the runner down the track? And, or what are some factors that affect that propulsive force? Well, obviously the runner's size and fitness, their strength, that's an important factor. I mean, not everybody can sprint at the same speed, so there must be some difference due to size, due to fitness, due to training. The runner's effort level in a 100-meter race, you're probably putting out maximum effort right from the start, but that effort level is controllable. So if it was a 400-meter race, you would not put out maximum effort at the start unless pain is something you enjoy. And then, you know, I leave it open to the students themselves. If they're new to modeling, they'll throw out some, let's say, questionable stuff. And this is where I provide a bit of guidance as necessary to say, no, we're not going to consider the phase of the moon and its effect on the sprinters. Well, I lead them to the Hillkeller model, where the propulsive force, first of all, it depends on a function P of t. I just call it a propulsion function. And that propulsion can vary between 0 up to some maximum value, P max. P max is where the runner is exerting maximum effort to propel themselves. 0 would be no effort whatsoever. They're just standing still. By the way, in this model, there's no backwards. We're just going to make progress in the positive x direction. M here is the runner's mass. We assume that this is part of the Hillkeller model in its simplest form, that the propulsive force a runner can exert is in proportion to their mass, under the reasoning that somebody who's twice as massive can, all else being equal, exert twice as much propulsive force. So that is the entire propulsive force model right there. Mass times some function P of t. And we are going to assume, given that it's a sprint, that the runner exerts maximum effort throughout. If you look at the dimension of this thing, and I like to point this out, P has the dimension of acceleration. You might think of it as the maximum acceleration the runner is capable of from a standing start. That's one way you could kind of begin to wrap your brain around it. And like I said, we're going to assume that it's maxed out throughout the race right from the get-go, because this is a sprint. The resistive force. What are some factors that affect the resistive force? So again, we take a poll in class, people throw out ideas. Well, obviously the first things they throw out are air resistance, or the body's own internal resistance to motion. Those are obvious things. And of course, what do they depend on? I asked them. Well, it depends on how fast the runner's going, right? You run faster, presumably there's more resistance. It might depend on the runner's size, like the propulsive force. And after paring down their ideas on what factors are important, I kind of gently lead them to this model that's traditional in the Hillkeller model. The resistive force is proportional to V of t, the runner's velocity down the track, the mass of the runner, and the idea here is in the Hillkeller model, the resistance is kind of thought of as an internal resistance of the body to motion. So a runner who's twice as big, has joints that are twice as big, twice as much internal resistance to motion. That's sort of the rationale behind it. And then there's a constant of proportionality there, and the minus sign there. So K is a non-negative constant, and I put an explicit minus there because it's supposed to be a resistive force. Well, you take that as the model in the Hillkeller, and the students say, well, I thought air resistance was proportional to quadratic in speed. And I can say, well, we can pursue that later, and you can, but in the usual model, V of t it's linear. The resistive force is linear in V of t. And I also point out the value of having a model that's easy to analyze. So if it yields ridiculous results, then you can go back and say, let's try something harder. Well, you put it all together. Mass times acceleration equals the net force on the runner, and you're led to that equation that you see there. I have the students write this out, and then I tell them to simplify it. And of course, the first thing they say is, hey, the way we've chosen to do this, M cancels out the mass of the runner. We don't need to know Usain Bolt's mass. It doesn't matter. So you divide out the mass, and you're led to this simple first order ODE. And when I teach ODEs, and I use this as my kickoff, this is usually the first differential equation they've ever seen. So there are infinite, and then I have them verify there are infinitely many solutions to this ODE. There are infinitely many functions that satisfy this, and I have them verify that taking P max over K is a constant solution to that ODE. And I asked them, what does this mean? Well, this is where the runner runs at constant speed throughout the race, and it turns out it's the runner's maximum speed. That would be running through the starting line. That's cheating. I have them verify that this function also satisfies that ODE, and that's in fact the one we pursue because that's the one that corresponds to the runner starting with no velocity at time 0. So I have them verify there are infinitely many solutions to that, and then I kind of lead them to the idea that we need an initial condition. If we have infinitely many solutions, we have nowhere used the fact that the runner started at the starting line with 0 initial velocity. And so if we start, and then I look, if you look back at Usain Bolt's data, his race really didn't start at time 0. It started at time 0.165 seconds, which if we know that, we might as well use it. So I have them, so then at this point, this is like day 1 of the class to kick off ODEs. At this point, I would have them, we'd pause while we contemplate, how do you figure out the solution to an equation like this? So this leads us to integrating factors or separation of variables, maybe both. I tell them, we're going to figure out how to analyze this ODE, and then we're going to come back and contemplate whether it does a good job at modeling a sprinter. So in between the last 2 lines on my slide there, there's at least a week of class, but we are led to the following formula for the velocity of the sprinter if they start with velocity 0 at time t0. And now that we know the sprinter's velocity, we can, well, if you look at that formula right there, there's that unknown constant K in play, and there's P max, the max propulsive force that the runner can exert. We don't know what either one of those is. We know what T0 is, at least for Usain Bolt's race. So there are some unknown parameters in the model that have to be somehow determined, either measured or estimated. Well, I tell them, and this is in the literature, P max, the max propulsive force, or more accurately, the max acceleration that a world-class sprinter is capable of, is about 11 meters per second squared. That's been measured in the lab. So just to avoid having too many unknowns floating around, I just say, let's go with 11 meters per second squared. So the runner's velocity is given by the formula you see there. T0 is known to us. K is not known to us. We're going to have to somehow figure out K. We're going to do that by comparing this model to Usain Bolt's data to estimate, at least for him, what was K. Now, the data we have is not velocity, it's position. Well, so what we need to do is we need to compute the position of Usain Bolt, and it's a simple integral, just integrate, and you're led to this formula here, and I write x of t comma k just for convenience to indicate that x depends on t and k. T0 is known to us. That parameter k is what we'd like to estimate from the data. At this point, depending on how sophisticated you want to get, I used to just tell them, let's take a wild guess at k, plot this function x of t, and compare it to Usain Bolt's data, and just do a fit by eye. You can do that, and it works reasonably well. Here's what you get. If they play around with it on their computers, I've got them running Maple in class, k equals 0.93, they all gravitate to that value there and say that does a really good job. It doesn't fit the data perfectly, doesn't nail it, but it's bloody good. So that if you didn't want to do anything fancier, like I used to not do, I'd say, okay, let's go with this. And now, and actually in some sense, there's our validation of the model. Look how good that is. But I like to give them techniques for estimating parameters that are a little less subjective. The one thing I point out to them is everybody picked about the same value, but it's a little subjective if we're trying to fit parameters in this matter. Is there a more official procedure we could do? Well, there's our function x of t comma k again, and we would like to choose k. In a perfect world, we could choose a value of k so that function nails the data. Every single one of the 10 data points we've got, that would nail every single one of them. In a perfect world, there would be a single choice of k that satisfies essentially 10 equations in one unknown. There they are. There are the 10 equations written out in the form of x at a given time, x at a given position equal minus a given time. Well, actually, I think I got my times and positions backwards there. I do. Oops, I transposed the, well, in any case, you get the idea. I got 1.85 where I wanted 10 and 10 where I wanted 1.85. In any case, it's 10 equations and 1 unknowns. There's not going to be a solution. There's not going to be any value of k that satisfies that. Instead, what we want to do is, instead of trying to satisfy all the equations simultaneously, form this sum of squares here, where S of k, I essentially take the first data point and look at the discrepancy in my model versus the required condition, and I square them all and add them all up. And so I kind of lead them to this idea gradually that we would love it if we could pick a value of k that makes S of k equal to 0, but we can't. That's 10 that would require us satisfying 10 equations and 10 unknowns. Well, instead of looking for a value of k that makes S of k equal to 0, why not just try to minimize it? Try to solve all 10 equations as best you can with an optimal value of k. And if you look at k, I convinced them, you can easily, I'm going to show you a plot of k on the next slide. You can easily see that S of k is bounded below by 0. It's a sum of squares. And it seems highly likely that S of k should have at least one minimizer. So you plot it. And that's what it looks like when you plot that function S of k. And that shows you how well any given value of k fits all 10 data points. And it's pretty clear there is a real winner there. And it's precariously close to the value that the students decided upon when they did a visual fit to the data. So you minimize it. And it turns out, well, they choose 9.93 visually. Well, the official minimum is 0.928, but that's essentially effectively what they found. And it yields a residual of 1.544, which at the moment means nothing to them, but later on, the idea of a residual can be useful for doing certain other types of analysis. In any case, if you go with 0.928 as your optimal value for k, there's your predicted position for Bolt's position at any given time. And I have data from other sprint races from both men and women at different high-level competitions. And each one yields a different value of k. And anyway, this is Bolt's optimal position. And if you plot that, it fits the data very well. But once you've got this in hand, you can now use it to do some prediction, even some extrapolation. You could ask how fast could Bolt run 200 meters? You can solve x of t equals 200 for t and predict. It turns out that it predicts that Bolt could do 200 meters in about, I think it's 18.9 seconds, something like that. And his best is 19.2. So of course we can then quibble over why is it different? What's different about 200 meters than 100 meters? Why would it be a little slower than predicted? And the students sometimes point out, well, you run the 200 around a curve, and that does slow runners down. Or you could predict how fast could Bolt run 100 yards, which is close to 100 meters, but not the same. Or you could ask how fast could he run a marathon? And of course, for a marathon, it predicts he could run it in about 40 minutes, which of course is ridiculous. But then, of course, we talk about models have domains of applicability, and you can't sprint a marathon. Anyway, it leads to a lot of interesting discussion. So in conclusion, I found this gives students a kind of a fun real-world application. I've seriously thought about taking the students down to the track and having them run 100 meters, but I think I need like some kind of experiment, human resources experimental release to do that. It illustrates a point I like to make in DE, that whenever we construct a mathematical model, there are almost always parameters that have to be estimated from the data. And so I want them to have some idea of how you might go about doing that. In the Hillkeller model, there was this parameter P max, the max propulsive force for the runner. We had a lab measured value of 11, but couldn't we just estimate that from the data? And you can do that. Then you have a 2-parameter estimation problem, and it leads you into multivariable optimization, simple Calc 3 techniques. By the way, estimating P gives, instead of 11, it gives 10.38 for Bolt, which is pretty close and makes very little change in the fit to the data. And then I can ask the students to try various extensions of the model. I've done this from time to time. What if you wanted to modify it for distance running? what would change? I mean, you can't sprint. What constraints would you put in the model to indicate that someone can't sprint a mile? So that and there's been work on this too in the mathematical physiology community. So that's how I kick off. I've often used this to kick off DEs and give them a model right up front that they can start. It leads us somewhere to where, gee, here's a differential equation. I don't know what to do with this. We pause, we talk about solution techniques, and then we come back to it and we can do some analysis, some model validation. So that's my first model. I'm happy to take any questions and take a short break before I show you the second one.
I've got a question.
Yeah.
This is in your book, and I use this example day one as well. And I find I get a little bit of pushback from the students when you say, if a runner is more massive than, if one runner is more massive than another runner, all other things being equal, they can have more propulsive force, because I think students take it to the extreme in their mind and think of, a very obese person trying to run. And so if someone, if you get pushback on that point, how do you respond to that?
Well, I point out that the actual propulsive force, we write it as proportional to m, but also there's this function p of t that's the propulsion function, and it's clear that depends on runner training and fitness and natural ability. That's what I would say to them. I haven't actually gotten much pushback on the m thing, but that's what I would say is an obese person, if they were trained like Usain Bolt and they were all muscle, they could probably exert a big propulsive force. Also, it seems, and I've raised this with the issue. This is something I bring up in class. It seems to me that, why did Usain Bolt win the race? Did he have a bigger Pmax value? It seems like maybe why not K? Why is K the parameter that couldn't we treat K as a constant for all runners? And the propulsive force is what really varies, that distinguishes one runner from another, their conditioning and their natural ability. You could make that argument. So I've thrown that out to students before, but I've never really done anything with it. Yeah. Bryan.
Oh, hi again. I was just wondering if you've developed projects based on optimal running strategies.
Well, that I haven't. I have. God, it was so long ago, and I can't remember what the conclusion was. It wasn't in DE class. It was in a math modeling course. One of the students did some research on exactly that, how the model has been adapted to distance running, and then it's an optimal control problem to say, how can I get to the end of a 10-mile race as fast as possible? Should I go fast at the start and tough it out? Should I start slow and go faster? Should I run an even pace? I know there's been work on that, and these optimal control problems are a little bit much for a second-year DE class probably. But yeah, that's exactly an interesting thing. I almost thought about putting stuff like that in the book, but it just got too much.
Yeah, that would be a great project, because I actually use your book for a mathematical modeling course.
Oh, okay, good. Yeah, that would be. That would be really fun to do.
Right.
And this student did something with it. I can't even remember. It was 1996 when I did that.
Oh, okay.
Yeah.
Okay, thanks.
Sure. Anything else? Are we just going straight through, or do we need to wait is there like an official designation for starting part 2?
I think you're just scheduled to go straight through. Like in the schedule, it doesn't split it into 2 parts. So you might be good to go, or if you want to wait till 2:30, we can.
Oh, I'll go. All the slides will be available in case anybody misses a little something. So, okay, let me stop sharing for a minute and pop open another set of slides I got here. Where'd I put them? Here we go. Okay, and all right, I will begin talking about the next topic I like to do. So I'm sharing screen again, and I'm popping it to full screen mode. I assume everyone can see that. Okay, very good. So this is, again, this is another little something I put in the book that I kind of flirted with over the years in my DE course. Here's the background. We do the Laplace transform. We're an engineering school. We do the Laplace transform in our DE1 class. And, you know, people try to sell the Laplace transform as it turns differential equations into algebra problems. And it's true, and it is a nice unified framework for thinking about, oh, here's a differential equation. Now it's algebra. Solve the algebra problem. Go back to the time domain, as the engineers would say. But in the end, the students, they seem a little like you just showed us a new technique for solving DEs that we already knew how to solve. Now you can add the more compelling argument that, yeah, but now you can handle step functions or Heaviside functions, and you can handle Dirac delta functions in a unified framework. And that is a reasonable selling point. Although I do point out to them that you could do that. You can do those things without the Laplace transform too. You can do them just with a hands-on approach in the time domain. But the Laplace transform is very useful for that. So I was always looking for some really compelling application where if you don't have Laplace transforms at your disposal, you're kind of toast. And control theory, classic PID control theory is an example of that, where it's so much easier to analyze things by Laplace transforming everything in sight, analyzing them in the so-called S domain. And in fact, the engineers will typically work entirely in the Laplace transform S domain and never even look back at the time domain. So here's an example I've used in class that I think illustrates that. An incubator. So an incubator is basically a glorified refrigerator. Many of them can heat all of them can heat their interior. Some have active cooling elements. And I'm going to assume that we have an incubator. It's supposed to hold biological specimens in a lab and hold them at a precisely controlled temperature. So I'm going to use the example of an incubator that's supposed to keep its interior at a constant 80 degrees Fahrenheit. But of course, the environment in which the incubator sits is not 80 degrees. It might be, it's 70 degrees or room temperature. So here's a picture of an incubator I stole off the web. And we have tons of incubators here in our biology labs. So it sits in a lab with a certain ambient temperature that may not be constant. But the incubator itself has the task of precisely controlling its interior temperature using a heating and cooling element. So question is, how should the element be controlled to maintain the interior temperature of the incubator? It's not as easy as it sounds. It's not as easy as it sounds. So here's what we're going to do. We're going to model this system with a linear ODE, basically Newton's law of cooling. We're going to assume the incubator obeys Newton's law of cooling. We want a control strategy for the incubator that causes it to behave in a certain way, even in the presence of unforeseen disturbances in the language of control theory. So, and this is not special to the incubator. There are many examples of technology that where you want to control the system to a desired end. And so that's what we're looking for here is to control the incubator to make it stay at a certain temperature, even in the presence of an unpredictable environment. Many of the problems like this, and I'll give some more concrete examples later, they use what's called PID control theory, and it relies heavily on the idea of the Laplace transform. PID is probably, it's ubiquitous in technology, and it's a great application of the Laplace transform, where the Laplace transform makes your life so much easier. So let's look at an incubator. Let's say it's sitting in a lab that's at a constant temperature of 70 degrees Fahrenheit. We want the incubator's interior to stay at 80 degrees. But of course, if you don't do anything, if you have no heating or cooling in the incubator, it's going to cool down to 70 degrees, basic thermo. So one strategy for making the incubator stay at 80 degrees, assuming it has the ability to actively heat and control itself, just set that heating element so that it precisely balances the heat loss to the environment. So you'll have a steady state condition. Set it so it keeps the incubator at 80 degrees under the assumption that the lab is at 70 degrees. Have the thing run at that constant power level. This is an example of what's called open loop control. Set the control at a given level and then forget it and hope that everything stays constant. Well, let's look at what happens here. Here's my model for an incubator. It's Newton's law of cooling with an ambient temperature of 70 degrees. K is the cooling constant, some positive constant, and Y of T is the incubator's temperature at time T. Let's assume that that's the model for how the incubator will behave if there's no control. If there is control, I'm going to implement that control by adding a function U of T to the right-hand side of Newton's law, and that U of T has the interpretation of being the input from the heater. Now you can do some dimensional analysis and find out how to physically think of U of T, but I don't want to get bogged down in that at the moment. U of T is a function that if it's 0, the heating element is off. If it's positive, the heating element is on. It's actively pumping heat energy into the incubator. If U of T is less than 0, it's actively cooling the thing. So our task is choose U of T so that the incubator stays at 80 degrees. Well, in this case, if the lab temperature stays at 70, this is easy. And just to be concrete, let me take K to be 0.05. If we're working in, say, degrees and hours, that actually you'll see that gives a semi-plausible result. The desired incubator temperature is 80 degrees. Let's suppose that the incubator at time 0 starts off at the correct temperature and there's no control. The control unit is turned off. Here's what will happen. Now, this is, of course, a trivial first order ODE that the students can solve at the point I start talking about this topic. And of course, it's just solve Newton's law of cooling in the usual procedure. The incubator cools down to 70 degrees slowly over time. Okay, that's bad. We want it to stay at 80 degrees. So obviously we have to turn the heating element on. What level should we turn it on to? Well, whatever level will keep the incubator at 80 degrees. So what you do is choose U of T to be a constant and make it a constant so that Y of T is a constant solution to the ODE under consideration. In other words, assume Y of T is 80, of course, that means Y prime is 0. Plug that information into the red equation and you find a simple equation you can solve for U of T. You should turn the heater on to level 0.5, whatever that means in the physical context here. You should turn it on to that level and leave it there. That will keep the incubator at 80 degrees. This is open loop control. Of course, there's my very informative graph of an incubator that's at 80 degrees. So this will work perfectly if nothing changes. However, if the ambient temperature in the lab drops at some point, somebody opens the window or changes the thermostat. Let's assume that at time 20, somebody opens the window and the lab temperature drops to 65 degrees. The control for the incubator is set at a constant 0.5. It doesn't recognize that. The temperature of the incubator begins to fall below the desired 80 degrees. That's bad. Okay. Now, this is an example of what in control theory they would classically call a disturbance. Something in the system, something has changed, and we need to be able to adapt to it. The problem is open loop control doesn't adapt to unexpected changes. This could be, so the lab ambient temperature changes. Like I said, somebody opens the window. Someone opens the incubator door to get something out. The incubator's thermal load changes. Maybe that'll change how things behave. There's more or less stuff inside. Or, things degrade over time. Door seals leak, insulation degrades, heating elements age. The control strategy that we're using, open loop control, can't deal with any of that. It just keeps going at level 0.5, 0.5, 0.5, no matter what. The lab could be on fire. It will stay at 0.5. Okay, what we need is to alter our control strategy so that the incubator can monitor its interior temperature and recognize when it's off target, and then feed that information back into the control strategy and say, uh-oh, the temperature's falling, turn the heater up. Or the temperature's too hot, turn up the cooling. This is called feedback or closed loop control. This is where it gets interesting. What's your strategy for saying the internal temperature of the incubator is this, but I want it to be 80 degrees? What should I tell the control strategy and the heating element to do? Well, the simplest one, and the students themselves will hit upon this with a little prodding, is called proportional control. If the incubator's temperature falls below 80, turn up the heat. If it's above 80, turn up the cooling, but quantitatively, how? Well, do this. It's called proportional control. So take the heating element, turn on the heating element to given by this formula here. K sub P is a constant called the proportional gain, 80 minus Y of T. If you look at this, if you look at what's in red there, if Y of T is below 80, then U of T will come on to a positive level. If Y of T goes above 80, then U of T is negative, and that says turn the cooling on. And if Y of T is 80, U of T is 0. It says don't do anything, you're at the right temperature. It looks like a very sensible control strategy. It leaves something to be desired, as you'll see. And it's kind of surprising, but this is called proportional control. So it's very easy to analyze this control strategy. You don't need Laplace transforms. You can do this. You can do this in the first week. As soon as they know how to solve linear DEs, you can do this. Notice that I want you to point out one thing. U of T no longer depends on the ambient temperature. This doesn't require the ambient temperature of the lab. It just says, are you, to the control strategy, are you on target 80 degrees? If not, do this. Well, let's analyze it. In our ODE, the ODE that we have before, the controlled ODE becomes this. Okay, you've got two terms now. The Newton loss to heat loss to the environment, and the control function U of T there. And notice that this is, with a little rearrangement, this is just a simple linear constant coefficient ODE. You don't need any Laplace transforms to solve this, and you can solve it quite easily. And if you look at it, I'm going to take that constant K sub P. Let me pop back. I'm going to take K sub P to be 1, just to pick something. Okay, I take K sub P to be 1, and here I show two scenarios. Number one in blue is the no control strategy, the open loop strategy, where the lab is at 70 degrees, the heating element is set to 0.5, and it just stays at 0.5. That's the case we looked at previously, open loop. And so with that open loop strategy in blue, the heating element keeps the interior temperature at 80 degrees until, I assume at time 20, suddenly the lab temperature has dropped 5 degrees. Well, the open loop doesn't know that, so it just, the temperature inside plummets as the open loop stays at its constant 0.5 heat input. Now, look at the red curve. That's our proportional control strategy. In some ways it's better, in some ways it's worse. It starts off at the correct temperature, but even when the system has no disturbances, the lab has stayed at 70 degrees, the open loop control falls to 79.5 degrees. It does not maintain the constant temperature that's required, even when there are no disturbances in the system. At time 20, when the lab temperature suddenly plummets, well, the open loop, or the proportional controls, does a better job now. At least you see it recognizes that something's off, and it tries to control for it, and it keeps the temperature from falling too far, but it's not staying at the required 80 degrees. And this is a generic problem with this very simple proportional control strategy. It looks very reasonable, but it's biased. And in fact, you can analyze, or have the students, you can have students analyze, why is it biased and how biased is it? Well, you do a little analysis. You take this controlled ODE, that's the one that we solved in the last slide. Take K sub P to just be, I took K sub P to be 1 in the last slide, but you can take it to be anything you want. And if you do a little analysis, you find that the equilibrium solution to this ODE, the temperature that this proportional control is going to stabilize it at, is not 80 degrees. There's a bias involved in it. It's going to stabilize at 80 degrees minus this expression here, where K sub P is whatever you chose for the cooling constant, or for the proportional gain. And in the case we were looking at, where K sub P is 1, it turns out it's going to stabilize at about 79.5 degrees. Now, if you look at this expression here, this bias expression, you can say, well, we can minimize that bias by just taking K sub P to be something enormous, in which case this whole term will go to 0. Well, if you take the proportional gain to be huge, that says that that if the temperature is running a little low, turn the heating element onto an absurdly high level. It's not practical. You'll burn out the system. We'd like a control strategy that does what this is trying to do, but stabilizes at the correct value. This leads us to a slightly more sophisticated control strategy that's called proportional integral control, or PI control. So here's what we do. We're going to augment our control strategy. We're going to take the control function to be the proportional control we had before, and we're going to throw in a new term called an integral term, PI for proportional integral control. That term you see in red, so Ki here is a constant called the integral gain for the system, and that term you see in red, well, it depends on the the 80 degrees is the desired set point temperature. Y of t is the current temperature, is the temperature over time, and what this does is it integrates any discrepancy in this. So if Y of t is running too low, this term, the blue term, the proportional control will come on and say, warm it up. But this integral control has an additional warming effect. If Y of t is running too low and it stays too low, if it's consistently low, the integral is integrating that over time and winding up the control to say if it's persistently low, it keeps cranking the control up, trying to drive that bias out of the system. Or if Y of t is persistently too hot, this integral will run consistently negative and build up until U of t gets sufficiently negative to drive the temperature back to 80. Now, of course, it looks good on paper. Does it do what's desired? Will it eliminate the bias in the system? This is where it gets interesting. This is where the Laplace transform becomes kind of indispensable to analyze this system. So what we do is we take this control function, U of t, and we jam it into our ODE. And here's what we get. So we take the ODE that we had previously. So we've got the uncontrolled ODE would be simply the terms in black. The blue terms there, that's the proportional control. And now we throw in the integral control and in red. And U of t consists of the proportional term and the integral term. And so you throw this on the board and you tell the students, don't panic. Because although it looks terrible, it's an integral differential equation for Y of t. At this point, we have studied the Laplace transform for a while, and we know that a term like this, an expression like this, can be Laplace transformed. It has a simple Laplace transform, just as derivatives have simple Laplace transforms in terms of Y of t's Laplace transform. So do integrals of this form. So I point out to them that although this looks terrible, if we Laplace transform it into the S domain, the terminology I like to use because these students are mostly engineers, this terrible integral differential equation is going to become an algebra problem, just like any other differential equation. So you take this equation, there it is again in its full glory in the time domain, hit it with a Laplace transform. All the derivatives are gone, and you now have a big algebra problem. What do we know here? We know we have a choice for K of P, we have a choice for K sub I, and the only thing we have to do is solve for capital Y of S, the Laplace transform of the system's response in time. We also have an initial condition here, and then inverse transform. So you do that. What happens? Well, it's a simple variation of what they've seen at this point, how to solve differential equations with Laplace transforms. Well, here's what you get in the present case. I just took the two control gains to be one just for convenience. I assume the controller starts off at the system starts off at the correct temperature of 80 degrees. And in the present case, here's what you get for the Laplace transform of the solution. Now, you could do an inverse transform. Of course, I have them do simple inverse transforms by hand. Something like this, I would just say, feed it to the computer, an inverse transform, and tell me how the solution behaves as a function of time. Here's what the system looks like. This is the no disturbance system. Now, this is where the system starts off at the desired 80 degrees. The lab temperature is 70 degrees. If you look at this, you say, hey, your controller dropped a quarter of a degree right off the bat. Well, that is true. That's where the proportional portion of the control is still in force, and the integral part hasn't wound up yet. So it does begin to drop, but eventually, because the system is running too low for some period of time, the integral part begins to wind up and tells the heater, come on, turn on, and it drives the system back to the desired temperature. Unlike proportional control, which stabilized at 79.5 degrees, the proportional control stabilizes at the correct 80 degrees. And you can prove under very general circumstances that proportional integral control will stabilize at the correct temperature. Now, this is the system with no disturbance. Everything's going according to plan. What does it look like if the lab temperature suddenly drops 5 degrees at time 20? It looks like this. Here's what PI control does. So up to time 20, this is the same as the previous graph. Everything's stabilizing at 80 degrees. Somebody opens the lab window. The temperature in the lab drops to 65. The temperature of the incubator begins to drop. But look at it, it only goes down 0.15 degrees before the controller stabilizes it at the desired 80 degrees. So this is a kind of feedback control that is more effective than simple proportional control. And then and the beauty of this is you can have the students see that, my God, how would I have dealt with that equation without the Laplace transform? Here, I'll pop back to that previous slide right there. If you look at those guys, how would you deal with this time domain integral differential equation without the Laplace transform? It's not entirely clear what you do with that. But in the Laplace S domain, it's an algebra problem, just like any DE, linear constant coefficient ODE. So anyway, it gives them, and many of the students are in, our students taking DE are in their second year. All the MEs and double E's and the chemies know that they're going to take a controls course, so they're motivated to understand this. And then so some conclusions and some other things I've done. You can. This is PI control. The more general term is PID control. D is for derivative. You can throw derivative terms into the control strategy, and derivatives Laplace transform just as nicely as anything else. So you can have them look at more generally at PID control, and you can have them start experimenting with those gains, the proportional gain, the integral gain, and then there's a derivative gain. And you can have them look at how those parameters affect the system. I don't go too far into that because that really gets into what's control theory and what people call tuning the controller. But it does show them that there's some interesting mathematics here. And of course, you can ask. I have them do all kinds of experiments. What if the set point of this system itself has changed? How does the controller respond? We said we wanted it at 80 degrees. What if we suddenly decide the samples should be held at 90 degrees? Now, how will the system respond to that? And again, the control parameters. If you choose your control gains poorly, it actually destabilizes the system. For example, if you're really dim-witted, you choose KP to be negative, which says to the controller, if it's running too hot, turn up the heat. If it's running too cold, turn up the cooling. That leads quickly to a runaway exponential blow up in the system. The system is completely unstable. But even more sensible choices for the control parameters can lead to strange instability. So this is exactly what I was talking about. Control tuning the controller. How do you choose those constants to give the best response? And then the engineers themselves would very much approach this in the Laplace domain right from the get-go. They would not even write down that horrible integral differential equation. They just view it straight away in the Laplace domain, and they use the language of what are called block diagrams, transfer functions. And I actually put this in the Simio textbook. And it also, this can illustrate the value of looking at the Laplace transform as a function of a complex variable, because the stability of the system, the stability of the control strategy, it depends on the location of the poles of certain functions involving Laplace transforms, the so-called transfer functions. It depends on where they lie in the complex plane. If they lie in the right half plane, you've got a bad control strategy. It's unstable. If they lie in certain other areas, your control may be stable, but it may oscillate wildly. So last quarter, I actually did a variation on this, where instead of trying to design an incubator control, I had them design a cruise control for a car that would hold it at a steady speed. And I had them play around, and they found that certain control strategies, yes, they would keep the car at 60 miles an hour, but they do it by oscillating slowly or between 80 and 40 miles an hour and slowly gravitate to 60. That's not a good control strategy. So, and then I put some other stuff in the book that active controlling a vibration isolation table or balancing the upside down pendulum, like trying to balance a Segway type scooter so it's stable. That's a nice control theory problem. So this is something I do that you can take as far as you want to show students that Laplace transforms are really kind of indispensable for certain problems. So that's what I wanted. That's my second scenario. Happy to answer questions.
Are there any questions for our speaker?
Yeah.
Go ahead, someone.
I was first, that was a wonderful presentation. I think really gets me excited about teaching the next time I teach Laplace transform.
Oh, cool.
I really enjoyed that. And I was wondering on the controller tuning part.
Yeah.
And I might have missed something right there at the end. What is the mathematics or that would help us solve for the optimization there?
Oh, well, it all comes down to, for the most part, where do you put the, so there's a transfer function in this system that tells you how the output depends on inputs. It's a function of a complex variable. It's basically, it's obtained via Laplace transforms. Where the poles of that thing lie dictate the behavior of the system. And there's different strategies for choosing the optimal parameters. There's in fact an entire cottage industry that revolves around tuning PID controllers. And actually, I've looked at the stuff before, but I don't know much about it. But if you go Google tuning a PID controller, you will find 6 million references. Some of them, companies that have their own tutorials on here's our strategy for tuning PID controllers. There's just a vast amount of stuff on that. I just have the students play around, and to emphasize, if you do it bad, you get terrible. You'll get a system that blows apart or oscillates wildly, getting the best controller, that depends on what you mean by best. So yeah, I don't know. I would go Google that. I don't have any ready response for the strategies that are used.
Great, thank you.
Sure. Bryan?
Oh yeah, I was wondering. Also, just like Cecile, I guess, who put in the chat, what software did you use for the numerical implementations here?
Let me stop my share here for a minute. I use Maple we use Maple in class. That's all I use is just Maple. Although I put this in the book. I put this project in the book. On the software website, I have software that supports these control computations in each of Maple, Mathematica, MATLAB, and Sage, just using elementary symbolic analysis. Of course, MATLAB has an entire controller toolbox that's dedicated control theory, but that's too much probably for this. Is the goal here is not to turn them into control theory experts. It's to emphasize the Laplace transform.
Sure. Also, I was wondering for the numerical implementations that you showed and the visualizations when the temperature drops.
Yeah.
Did you implement just this by basically implementing a non-constant ambient temperature and then finding the solutions numerically?
Yeah. Well, I didn't even do it numerically. You can the temperature dropping that you can just model with a Heaviside function and everything Laplaces nicely.
Okay.
But you're right. You're right.
If you had a Heaviside function symbolically.
Pardon?
I'm sorry. So you did this symbolically, just using the Heaviside function for the drop.
Correct. I just did it symbolically.
Okay.
Yeah. Now, one of the things when I did the cruise control version of this for a car last quarter, all this PID control theory revolves around a system that's governed by a linear differential equation. So I had to posit a linear model for how a car responds to resistance. Like the Hillkeller thing, I assume that the force of resistance the car experiences is a linear force with respect to its velocity. So you can design a PID controller for that. of course, you can then ask, what if the car's response to air resistance is really quadratic? What am I going to do there? And I wanted to do this, but I ran out of time. In that case, you could say, well, let's suppose the car's response to air resistance is really quadratic. We can linearize that quadratic response at, like, let's say we want to keep the car at 60 miles an hour. Linearize that quadratic force at 60 and treat it as a linear air resistance, provided we think of it as a perturbation from 60 miles an hour. You can design a controller for that situation and then apply it to the nonlinear system. But that requires that you do numerical solutions, like you said, because you can't Laplace those guys. But then you can look at what happens if I design a nonlinear control strategy or a linear control strategy and apply it to an underlying nonlinear system. The answer is, if you don't go too far from the linearized point of operating point, it works well. If you do go too far, it might be a disaster.
Yeah.
And I did one like that in the text where you're trying to balance an upside down pendulum or a Segway scooter. That's the upside down pendulum equation is nonlinear. It's the pendulum equation. You can linearize it about vertical and design a control strategy to say, keep it near vertical, use the linearized equation, and it's fine. But if it goes too far off of linear, then the nonlinearity kicks in and the control strategy doesn't know that. And it ends up balancing the thing at like 37 degrees off vertical or something. I don't know. Anyway, so it's kind of an interesting thing to experiment with.
Oh, thank you.
Right.
Thank you.
So we probably have to wrap up right here because there's another session starting in 4 minutes. So we should go ahead and wrap up. So let's thank our speaker again.
Thank you.
Thank you.
And we will stop there.
Thanks, everybody.